Hello, hello, welcome back. It is lecture 4, Anisotropic Diffusion Filtering for Images. For this lecture series, we have preliminary taken a comparative study, a literature review of anisotropic diffusion. The paper name is Anisotropic Diffusion for Smoothing, a comparative study. This paper, it is a review paper in the abstract. In the previous class also we described anisotropic diffusion is a powerful image processing technique which allows simultaneously to remove noise and to enhance sharp features in 2 and 3-dimensional images. Anisotropic diffusion filtering concentrates on preservation of important surface features such as sharp edges and corners by applying direction-dependent smoothing. This feature is very important in image smoothing, edge detection, image segmentation, and image enhancement. For instance, in the image segmentation case, it is necessary to smooth images as accurately as possible in order to use gradient-based segmentation methods. If image edges are seriously polluted by noise, these methods would not be able to detect them, so edge features cannot be retained. Edge-preserving filters are used for smoothing an image while reducing edge blurring effects across edge like halos, phantom, etc. To introduce the concept of edge preserving, we begin with the nonlinear diffusion technique process by Prerana and Malik. In paper 10, they proposed a nonlinear diffusion method for avoiding blurring and localization problem caused by linear diffusion filtering based on the importance of image scale space representation introduced by Witkin. So anisotropic diffusion process is given by the equation 1. Then the change in the image will be according to the equation 2, where D controls the diffusion process. So in equation, the linear diffusion process is defined, and equation 4 from 3 can be derived as equation 4. So equation give Prerana-Malik filter and its diffusivity G square is given by equation 6. Then equation 7, the reflect estimation of edge structure is given, and in equation 8, Whitcurt in paper 15 proposed to choose the corresponding eigenvalues lambda 1 and lambda 2. This is given by equation 8. Now the anisotropic gradient diffusion, the change in intensity U over time is given by equation 9, and the diffusivity is given by equation 10. Now the anisotropic curvature diffusion is given by MCDE. Modified curvature diffusion equation is given by FT is given by equation 11, and the conductance modified curvature term is given by equation 12. Anisotropic diffusion using lattice basic reduction is given by equation 13, and the diffusion tensor, Whitcurt diffusion tensor is given by 13, and the structure tensor S is given by equation 14. Now, the additional condition are presented in original paper to obtain the equation mu I is given by 15, and the final equation, the modified one, is given by equation 16. We have discussed this one in the previous 3 lectures. Now the test image used is given by The following: the synthetic image in the normalized scale 0 to 255, the topographic primal sketch, then Lena image, CTA image, ROI CTA image is taken as test image. And in table 2, synthetic image with Gaussian noise is given, and their result is given in table 3. Table 4, age enhancing diffusion and conservative variant of EED varying lambda is given by in table 4, and table 5, smoothing error comparison is given in table 6. Topographic primal sketch for smoothing result is given, and table 7, smoothing error using 10 iteration, and in table 8, smoothing error using 20 iteration has been shown. And in table 9, smoothing of CT image has been shown, and in figure 1, intensity profile of CT image color figure outline has been shown. Using the three results, we compute smoothing methods for real image, Lena, and CT. The results are shown in table 9. A visual analysis presents a great similarity between the results obtained using gradient and curvature techniques with 5 iteration. The EED and CEED methods have better results than first two methods. To observe in detail the accuracy of the implemented methods, a raw image was selected to analyze the profile obtained by applying each of them with respect to the original image. To select the row of intensity, a scan of the original image was made and a row 84 was chosen, which crosses areas with low contrast and which are fundamental in the segmentation of nasal cavities. With respect to the Lena image, we select the row 256. The results were very similar to those obtained with the CT image. In general, the anisotropic gradient diffusion method attenuates image intensity in thin regions and does not maintain image edges. This can be seen the region enclosed by circles in figure 1. The green curvature represents obtained result. Anisotropic curvature diffusion method, Whitaker et al., presents a lower attenuation of intensities in homogeneous regions and preserves edges in a better way than the anisotropic gradient diffusion. Magenta curve in figure 1. But in thin region, both gradient filters and curvature filters attenuate region intensity. These drawbacks can be solved using anisotropic diffusion based on lattice basis reduction EED and CEED, which allows smooth homogeneous regions preserving edge and maintain intensity in thin region. Red and orange curves in figure 1. Conclusions. In this paper, a comparative study on anisotropic diffusion for smoothing has been presented to compare the methods, the root mean square error RMSE and the Nash-Stulif error or Nash error has been used. Numerical result for 2D images have been demonstrated that anisotropic diffusion using lattice basis reduction preserves more image information than the anisotropic gradient diffusion and the anisotropic curvature diffusion. Filters were tested on 3 images with different conditions, and the result show that in the low noise case, the anisotropic method based on lattice basis reduction performs much better than the anisotropic gradient and anisotropic curvature filters. EED and CEED smooth out the noise in homogeneous areas while still maintaining edge strengths with minimum blurring across edges. Furthermore, anisotropic filtering based on lattice basis reduction maintains intensity values in thin regions while the other two filters significantly attenuate it. In general, an anisotropic diffusion method based on gradient and curvature have drawbacks when regions are thin. In addition, edge accuracy is lost, resulting in increase of miscalculations by filtering applied after the smoothing. Now there are references are shown over there. These are the references. So for the references, first one is image selective smoothing and edge detection by nonlinear diffusion. Then it is sparse non-negative stencil for anisotropic diffusion, nonlinear anisotropic filtering of MRI data, then surface reconstruction from three-dimensional segmentation using implicit function, edge-aware anisotropic diffusion for 3D scalar data, anisotropic diffusion in ITK, then bias anisotropic diffusion, a unified regularization and diffusion approach to edge detection. Then it is a affine invariant detection, edge maps, anisotropic diffusion, and active contour. A brief survey of recent edge-preserving smoothing algorithm on digital images, scale pace and edge detecting using anisotropic diffusion, the art of scientific computing, then it is smoothing and numerical differentiation of cone calorimeter mass data, a multiscale geometry engine, on the choice of the parameters for anisotropic diffusion in image processing, a review of nonlinear diffusion filters, anisotropic diffusion in image processing, variable conductance, level set, curvature for image denoising, scale space filtering. These are the references that has been used in this paper. So we are concluding this paper, but in the next subsequent lectures, we will study more about this anisotropic filtering. So thank you for patient hearing.